In this part of the talk, I'll provide some very basic background on the topic of embeddings. Some of this background might be necessary in order to understand the rest of this talk. Specifically, I'll discuss semantic representation and the need for having semantic representations in natural language processing. Then I'll very briefly discuss one of the prominent models for semantic representation, which is called the vector space model. And then I'll discuss a very high-level view of the evolution of semantic representations in natural language processing in the past couple of decades. So the general topic here is artificial intelligence. And we all know that artificial intelligence aims at mimicking functions that are associated with our minds. In other words, the cognitive functions. Things that we do in our day-to-day life, like reasoning, planning, learning, perception, etc., etc., and the use of natural language, if we want to be very specific. We humans are able to communicate with each other, to verbalize what we have in our mind, or to understand what others mean, or what concepts other people have in their minds by the use of natural language. And when we say natural here, obviously it's as opposed to some artificial language like some programming language or some other synthetic language. And the basic idea in natural language processing is to enable computers to make the same sort of intelligence, to be able to use natural language in order to communicate with people, to understand natural language in terms of text, etc., etc., etc. And very broadly speaking, we can divide natural language processing into two broad fields: natural language understanding, or NLU, and natural language generation, or NLG. In NLU, the basic idea is to comprehend or to understand the meaning or the message conveyed by a piece of text, a sentence, a phrase, a word, a document, or larger pieces of text. And it's a symmetrical problem in NLG. The basic idea here is to verbalize or to transfer some internal representation of a concept you have in your mind or in the computer's brain, to express it through words, sentences, or in general through natural language. And there are many different challenges in both NLU and NLG that make NLP very difficult at different parts. One of the biggest challenges we have is ambiguity. And ambiguity resembles at different levels from different perspectives. For example, at the lexical level, the same word can be either a verb or a noun. Like, for example, the verb fly can also be a noun, etc., etc. But the same part of a speech, like the verb fly, can also have many different meanings. For instance, time flies, the pilot flies the airplane, and many other different meanings that are associated with the verb fly. And this makes it difficult for computers to understand the meaning of a word in the context. And usually the more frequent words are more ambiguous, which makes it even more difficult to understand texts. We can also have syntactic ambiguity, like I saw a man on the hill with binoculars. Did you see the man with your binoculars, or was the man with binoculars? So you can interpret the same sentence in different ways, and it's the same ambiguity that applies to humans when reading this text. It can also be metonymic, like New York voted for Biden. Was it the city itself, or was it the people in that city, or was it some committee in that city that voted for Biden? And also, we humans, when we make use of natural language, we make extensive use of some common sense knowledge background we have. For instance, look at this sentence: the tablet does not fit into my bag because it is too large. In order to attach it to either tablet or to bag, which is a problem called prepositional phrase attachment, we humans use some common sense knowledge we have gathered throughout our life by experiencing different things. And it's very easy for us to say that it was the tablet that was too large that didn't fit into that bag. But this attachment is a very difficult task for computers because this common sense knowledge or this specific knowledge is not explicitly encoded in this sentence. And this is some sort of knowledge that comes from experiencing the world or some common sense knowledge. We also have a lot of usages of figurative language like idioms such as all ears, fingers crossed, or other sorts of figurative language we use like sarcasm. Looking at NLG, we have similar problems, like we have ambiguity, because you have some concept in mind and you'd like to express it through words. There are usually many different ways for expressing a word, or many different ways you can make a sentence to express the same meaning. So it's a one-to-many problem here of ambiguity. Again, once you want to make the sentence, you can place the words in many different ways, and all of them can be grammatical, or maybe some of them are not grammatical. But which of them is the more fluent one to a native speaker? So these are all the questions you have to answer once you're generating some text, or you'd like to express some idea automatically. This takes us to semantic representation. Semantic representation is one of the oldest topics of research in natural language processing, and it lies at the core of both NLU and NLG. The problem here is to make computers understand the meaning of different pieces of natural language. So the goal here is to compute some machine interpretable form or some numerical form of semantics or meanings for different pieces of text, for example, a word, a phrase, a sentence, or a document. So in this example here we have for words, the goal is to attach some meaning to different words. For example, we're looking for some numerical representation for the word desk, some vectorial representation we will see shortly, that can denote the semantics of desk, that tells the computer that desk is something which is related to a table, desk is sort of similar to furniture in concept, and etc. For example, for the word pizza, the computer takes some meaning for that, like pizza is a food, pizza has a rounded shape, etc., etc. If we don't do that, a word like library is a sequence of characters to a computer. And each character, depending on the encoding you use for storing that text, is a set of bits and bytes, a sequence of bits and bytes, sequence of zeros and ones. And in this representation, even if you store the whole Wikipedia or millions of documents on a computer, and you ask a very simple question like, where are Himalayas? Even if you have hundreds of documents here talking about Himalayas, the computer will have no idea to answer that question because it has just a set of zeros and ones and it doesn't recognize even the question bit to answer that. And we would like to do that attachment of meaning to words. And vector space model is one of the oldest ways, or still one of the most prominent ways of doing that. Vector space model, or sometimes called term vector model, is an algebraic model for representing any sort of object. Here, words, sentences, documents, etc., as vectors. So here we have 4 words represented as 4 different vectors in a 3-dimensional, what we call semantic space. So semantic space is an imaginary space in which we place different objects for which we would like to have some meaning. Let's have a look at a simpler example. So here is a 2D, a 2-dimensional space, this gray rectangle here, in which we have a couple of words placed. If you look closer, you see that semantically related or semantically similar words are placed in the proximity of each other, like passenger train, station, railway, and bus and terminal, etc. And in other parts of the space, you have words talking about this domain of education, university, studies, library. And in some other part, you have fruit, flower, tree, seed, leaf. And the basic idea here is that semantically related words are placed in the proximity of each other, while they are at some distance depending on their relatedness to other words in that space. So here is a 3D example, the example we had earlier. And if you look closer here, is the fact is that each of these words are represented as a vector. And a vector is nothing but a sequence of real valued numbers. So this is one of the reasons usually this representation is called distributed representation. The examples we had so far were all toy examples. Let's have a look at a real example. So this is a 3D visualization of a semantic representation, a semantic space, specifically word2vec, the top 10,000 words, 10K. And the dimensionality reduction has been done using PCA. We have 10,000 words in this little three-dimensional space. Each dot is a word. And let's have a look at an example word like arsenal. So if I make it a 2D to make it easier to look, so if you see closer, all the words that are sitting in the proximity of arsenal are semantically similar words, like teams, like Manchester, like champions, finals, Wimbledon, or don't know things that I understand here, or many of the other words that are either in that domain of Premier League or football in general, or some of the words that are related to other meanings of arsenal. So if you look again at the three-dimensional visualization, this is a semantic space around the word arsenals and all the other words that exist, all the other 10,000 words in that space. Let's also have a look at the progress in the field of semantic representation and how the evolution happened in different models here in the past couple of decades. Probably the most intuitive way of having a vector space model for representing objects is to have a one-hot representation. In this specific example, we focus on words. And here you have vectors, you have representations that are as large as your vocabulary, the number of words you have in your model. And the idea here is that you have all zeros in the vector except one of the dimensions for which you have a 1. And different words have different indices for that 1, and that's the reason why it is called the one-hot representation, because you have a 1 and the rest are 0. But this is so intuitive and there are so many problems and limitations to this representation. You can do much better than this. For example, by collecting some co-occurrence statistics of words. If two words appear in the same context, you count it, and if two words appear in so many contexts together, then they are highly co-occurring and highly probably correlated in their semantics. And you can construct a co-occurrence matrix like this. Here, each row and probably each column can be taken as the distributed representation or the corresponding semantic representation of that word. But you usually do not use the direct representations here because they are usually very long in size, again, the size of vocabulary. So usually they are coupled with some dimensionality reduction techniques like the singular value decomposition or other ways of reducing the very large semantic space into a smaller space, like in terms of a few hundred dimensions. In the past decade, with the increasing popularity of neural networks in different fields, including natural language processing, we have had also some drastic change in the field of semantic representation. Specifically, we had word2vec, which is a very simple but efficient neural model for directly learning low-dimensional representation. The algorithm, which is in fact two different methods for doing it, CBOW and skipgram, which we are going to learn more in another part of this talk, had a high impact in semantic representation and in different areas of natural language processing in general. And there have been so many derivatives of word2vec with so many enhancements, a few of which we are going to cover here. And it was around this time that the term embedding almost replaced the term representation. So here you have low dimensional dense representations, which we usually refer to as embeddings. More recently, we have contextualized embeddings, in which the main difference is that the embedding is getting adapted depending on the context of the target word. So you have an embedding which is kind of sensitive to the context, to the sentence in which the target word is appearing. We have different models here like ELMO, but contextualized models are coming at the same time in 2017 with the introduction of a new neural model in specifically NLP called the transformers, which is nowadays probably the #1 choice in different NLP applications and tasks. In another part of this talk, we will go into details of transformers and all these different transformer-based models like BERT and many of the derivatives it has and all the intriguing properties they have. So here is the outline of this talk. In another part of this talk, we will talk about word embeddings, starting from count-based models, from dimensionality reduction techniques, going to neural models like the ones we call predictive models. We also cover character embeddings and different ways of enhancing word embeddings by using knowledge bases. We'll also slightly talk about cross-lingual models and finally about the different ways of evaluating word embeddings. In graph embeddings, we will talk specifically about the different models to embed nodes and relations in graphs and to convert this sort of representation of graphs into some sort of machine interpretable way of understanding that. In sense embeddings, we will focus on the meaning conflation deficiency of word embeddings, the problem they have in capturing different meanings of a word into a single vector. And we will discuss different ways of learning sense embeddings in order to address that problem. In contextualized embeddings, which is one of the longer parts of this talk, we will first provide some very brief background on the transformer model, the architecture that is being used nowadays mostly for learning contextualized embeddings. And we will discuss why we need contextualization at all. Then we will cover some of the techniques, some of the older ones like ELMO and context2vec, and then come to BERT, which is probably one of the most prominent models of semantic representation and NLP in general, and many of the derivatives it has had in the past few years. We will also discuss some of the analytical studies that have been done on different transformer-based models. Finally, we will talk about the evaluation techniques for contextualized models. In the sentence and document embeddings, we will discuss different ways of embedding longer pieces of text, including sentences, documents. And finally, in the ethics and bias, we will talk about some of the implicit biases or stereotypical gender biases we have in embeddings and some of the techniques that are available for debiasing, for addressing these biases.